Welcome students. In previous class we understood the idea of indefinite integrals. We understood what it meant by an area function. We also understood what is the idea of antiderivative. Then we defined the integral of f x dx as collection of all antiderivatives, this C belonging to a set of reals. Towards the end we understood the geometrical interpretation of this family of curves or the antiderivative. And we also looked at the area function from the perspective of integral, considering it as integral, which we said that this is a definite integral. So, these are the things which we learnt in our previous class. Today we will look at further that what are the properties of indefinite integrals, how can we evaluate the integral of a function which will be given to us. So, before we start, we take one example where I will show you the importance for the constant c which we take when we take the integral. So, suppose that we are asked to find out antiderivative f x of function small f x, which is given as 5 x raised to power 4 plus 2, such that the value of antiderivative is given to us. So, it not only says that we have to find out the antiderivative f x, but also it says that we have to find out that antiderivative which has the value f value as 5 when x equals to 1. So, out of the family of all the antiderivatives, we have to look for a particular antiderivative. I will show you how it can be done. So, from our previous experience of antiderivative of a function of the type x raised to power n, we can figure out that d by dx of x raised to power 5 plus 2 x turns out to be and therefore, this function is considered as the antiderivative. We need the antiderivative such that f of 1 is equals to 5, which will mean that 1 plus 2 plus c equals to 5, giving the value of c as 2. So, the antiderivative f x from here gives the value x raised to power 5 plus 2 x plus 2. So, in this case you notice that that we have got a unique antiderivative x raised to power 5 plus 2x plus 2, which gives you the value when x is equals to 1 as 5. So, if we are given a condition such that the condition which was given in this case as f1 is equals to 5, the specific value of that constant can be evaluated. In general, we consider this constant as any arbitrary constant. Next, we shall look at the properties of indefinite integrals. The first property relates, as we told initially, that integration can be considered as inverse process of differentiation. So, the property d by dx of integral f x dx is the function itself. That means that the integral of the function, and if you take the derivative of that integral, you will get the same function. Second property is that integral of the derivative of the function is the function plus a constant. Now, look at these two expressions first before we go for the proof of these equations. The first expression says that differentiation of an integral of a function is the function itself, while in the second case it says the integral of the differential of the function is function plus constant, and therefore, we do not say that the two operations, the differential and the integrals, are inverse operation to each other, but we say that they can be thought of as an inverse operation, because had they been inverse operation, then after application of both the operations simultaneously, they should have given you the function itself, but here in this case it is a constant. So, if we consider uniqueness up to the constant, then they can be thought of as an inverse operation. Proof. So, property A can be directly proved using definition. We know from the idea of antiderivative is that d by dx of f x equals to small f x, such that capital F x is the antiderivative of small f x, then integral of f x dx is capital F x plus c. So, now we will apply the derivative operator on this integral, assuming that capital F is the antiderivative for small f x. So, if we apply the derivative here, it will give us d by dx of integral f x dx will be same as it applied on the right hand side, d by dx of f x plus c, which is same as df over dx, because the constant derivative of the constant will be 0. So, and we already know from this relationship that df over dx is nothing but f x. So, d by dx of integral f x turns out to be the function f x itself. So, d by dx of integral f x dx is function itself. So, this shows property A. For property B, we again use the definition. So, we note that d by dx of f x, which is basically f prime x. So, now if you look at it again from the perspective of the definition of antiderivative, then small f x is antiderivative for f prime x, and therefore, using the definition of integral, we can write that integral of f prime x dx is f x plus c for c belonging to the set of reals, and this is what the same as property b, f prime x dx is equals to f x plus c. So, we have shown this property using definition that integral of a derivative is same function plus a constant. Second property which we will look at is that if we are given that the derivative of two integrals are same, that means that for two functions f x and g x, if the d by dx of integral f x dx is same as d by dx of integral g x dx, then both the functions integral f x and g x, they belong to same family of functions. How can we show that? So, what we do is that we take the entire expression. The expression implies that d by dx of integral of f x dx minus integral of g x dx 0. So, first you transfer this d by dx of integral g x dx to the left hand side, then take the operator outside and then write this expression in this fashion. Since this equality is true for all x and therefore, this equality is also true for all x, and this is possible that the derivative of some function of x equaling to 0, the possibility is only if the function itself is a constant, which means that integral of f x dx minus integral of g x dx is equals to a constant, let us say c, and which will mean that if I transfer g x on the right hand side, then the collection of all functions integral g x dx plus c 1, let us call it as c 1, such that c 1 is in R. And similarly, if I take the function f x on the right hand side, then integral f x dx plus c 2, such that c 2 belonging to R. So, they represent the family of curves for these integrals, and therefore, the two integrals, because these two families, because of this equality here, they are equivalent. So, we usually do not, as these families are equivalent, we usually do not bother about the constants which are written here, and we write that integral of f x dx is same as integral of g x dx. That means, the constant is omitted here. Further, we look for some more properties of integral operator. These properties are similar to the property of differential operator, which you have already seen. The first property is linearity property, which I will write in this in the following manner. Integral of f x plus g x dx is same as integral of f x dx plus integral of g x dx. Look at the functions. It says that the integral of sum of two functions is same as sum of the integrals of those two functions. The integral basically distributed on the sum. The proof is simple. What we do here is that you take left hand side and differentiate it. D by dx of the left hand side gives you as we know from property 1, which we have already shown, is that the derivative of integral is the function itself. So, using the property 1, which we have already proved, is that the derivative of this integral is nothing but f x plus g x. This we say that is relation 1, which is coming from the left hand side. Now, similar thing we will do on the right hand side, differentiate the right hand side. As we already know that derivative is distributive on addition, and therefore, we can write it as d by dx on integral of f x dx plus d by dx of integral on g x dx. Now, again using property 1, we know that d by dx of integral is same as the function f x plus integral d by dx of integral g x is the same as function g x. Consider is at relation 2. So, what we have shown here is that if we differentiate the two functions on the left hand side and right hand side, we get the same derivative, and from the property previous property they belong to the same family of curves, and therefore, this property is true. So, this proves that the linearity property on the integrals is followed. Second property is for scalar multiplication. So, what it says here is that integration of k times f x dx is same as k times integration of f x dx. Where k is some constant this also we shall prove using the same idea as we have done for the previous property. D by dx of the left hand side turns out to be, and the d by dx of right hand side we know that scalar k can be taken outside for the from the differential operator. Giving us again using the property 1. So, again similarly as in previous case, we claim that k f x dx is same as k f x dx. What we shall do now is that we shall club these two properties together and put them in a general formula. So, let us say for constants k 1, k 2 dot 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 k n and functions f 1 x, f 2 x dot 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 f n x. We have the relationship that integration of k1 f1 plus k2 f2 plus dot 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 kn fn dx is same as you take the k1 outside and integrate f1 sorry dx plus k2 and then kn fn x dx. This property helps in evaluating the integrals where the functions are written in certain linear combination. We will give you one quick example. So, suppose we are to find out the integral of the function ax square plus bx plus c. To find out the integral of this function, we write it in this fashion. Now, since we know the linearity property, therefore, we can write this a, b, c being constants here. A integral of x is squared plus b integral of x plus c times integral, and there is 1. So, therefore, we write it as integral 1 dx. We already have seen, or we can even use the method of antiderivative here, is that if we take the differentiation of x cube by 3, we will get x square, and therefore, this we can write as x cube by 3 plus b x, you have already seen that this is for x square by 2 plus small c, the integration for 1, that means if we differentiate x you will get 1, therefore, the function x should appear here, and finally, the constant. So, we will call it as c 1 because this c is already appearing here. So, it should not confuse us. So, the integral of this linear combination turns out to be this function, which could easily be evaluated by breaking this integral into 3 separate integrals and evaluating them. This technique will help us further in solving certain complicated problems. Now, we shall use our knowledge of differentiation and write certain formulas which will help us in evaluating the integrals during problem solving. These formulas are very basic formula, and you should try to remember them as much as possible. So, what I will do on the left hand side, I will write the corresponding formula of the derivative, and on the right hand side I will write the corresponding integral. So, we have this d by dx of x raised to power n plus 1 by n plus 1 as x raised to power n. So, corresponding integral of x raised to power n dx becomes x raised to power n plus 1 over n plus 1 plus a constant c. Here we must note that n cannot be equals to minus 1. We will deal with this minus 1 case separately, which will come in due course of time. As a particular case, we know that d by dx of x is 1, and therefore, the integral of 1 dx we have already seen, it turns out to be x plus constant. Certain trigonometric functions, for example, d by dx of sin x is cosine x, and therefore, integral of cosine x is sin x plus c. D by dx of cosine x turns out to be minus of sin x, therefore, we will put minus sign here. so that when we write the integral, it becomes integral of sin x is minus cosine x plus the constant d by dx of tan x is sec square x, and therefore, integral of, sorry I missed a dx here, sec square x dx equals to tan x plus c. These are all standard formulas which you can find in any of the reference book. D by dx of cot x is again minus cos sec square x, but I shall write it in this manner, so that it becomes integral of cos sec square x is minus cot x plus constant d by dx of sec x is sec x tan x, which gives you the integral of sec x tan x dx is equals to sec x plus constant d by dx of similarly cosec x is cosec x and cot x with a negative sign here, which again similarly as earlier I will take it here. So, that it becomes integral of cosec x cot x dx equals to minus cosec x plus c. Further, we shall look at the derivative of inverse trigonometric functions. So, we have seen it during previous class. D by dx of sin inverse x is 1 over square root of 1 minus x is squared, and therefore, the integration for 1 over 1 minus x is square root dx is sin inverse x plus constant, and also we have seen that d by dx of minus cos inverse x is also same as square root of 1 minus x square, and therefore, 1 minus. So, one should not get confused with the same function, because we have already shown you that these two functions belong to same family of curve, and therefore, sin inverse x and minus cosine inverse x they can happen to be the integral of same function. Further, we look at some more formulas as d by dx of tan inverse x. We know that it is 1 by 1 plus x square, and therefore, integration of 1 by 1 plus x square dx is equals to tan x plus constant, and parallel to that previous d by dx of cot inverse x is minus 1 over 1 plus x square, which takes minus here, and therefore, dx over 1 plus x is squared is minus of, so it missed here, cot inverse x plus the constant d by dx of sec inverse x is 1 over x square root of x square minus 1, and therefore, integration of x square root of x square minus 1 turns out to be sec inverse x plus constant. Similarly, d by dx of cosec inverse x with a negative sign equals to 1 over x square root of x square minus 1. Therefore, integral dx over x square root of x square minus 1 can also be written as minus of cosec inverse x plus constant c. So, with trigonometric and inverse trigonometric function, we have the relationship of logarithmic and exponential function. We have the knowledge of d by dx of e raised to power x as e raised to power x, which gives us the exponential of x integral dx same as e raised to power x. In fact, we can write that d by dx of e raised to power nx divided by n as e raised to power nx for n bigger than 0. So, that integral of e raised to power nx dx is same as e raised to power nx divided by n plus a constant for n bigger than 0, or rather n not equals to 0. The same is true for n negative as well, because as n becomes 0 here, this function will become 1, and we already know the integral for 1 dx, and we also know the d by dx for log of mod x, that is 1 by x, and therefore, integral of 1 by x dx will be written as log of mod x plus constant. So, this case which when we are discussing for x raised to power n not equals to minus 1. So, you can understand that the case when n equals to minus 1 can be taken care of by this formula. These formulas, let me remark that they are very important, and since they are very fundamental, so we should remember them, because we will be using them very frequently. One more important remark which I would like to put here before I proceed with the example is that it may not be possible to find out the integral of all functions in terms of elementary functions. There may be some function for which we may not know that what is its antiderivative by inspection or even by evaluation. One such example may be e raised to power minus x square dx. So, finding out that the antiderivative for this function in terms of elementary function, that means that polynomial, trigonometric, inverse trigonometric, exponential, etc., is not possible. So, certain cases we may not be able to evaluate, and in those cases we leave indefinite integrals in their own form as they are. So, now we shall look at some examples depending on the properties and integrals which we have learned. The first example that I have chosen is very simple. To find out the integral of the function 4 e raised to power 3x plus 1 dx. So, if you look at this integral, first of all it is sum of two functions, and therefore, we use the property of distributive nature of integral on summation and write it in this form: e raised to power 3x taking constant 4 outside plus second integral 1 dx. Now, from the formula we know e raised to power nx. So, integral of e raised to power 3x dx turns out to be e raised to power 3x by 3 plus constant. So, we will put it as integral e raised to power 3x by 3 plus 4 times that constant. So, we will call it as 4c1 plus integral 1, this we already know that this is integral x plus the constant c2. So, that the entire term becomes 4 by 3 e raised to power 3x plus x plus 4c1 plus c2. Since c1 and c2 both are constant, so we can club them together and we can rename them as a new constant. So, it will become 4 by 3 e raised to power 3 x plus x plus a constant c. So, the integral turns out to be this much. Now, here you can also do that while integrating, either you substitute the constant when you are integrating an integral, or you can also do that you can substitute the constant at the end. So, many times we do not we may not substitute the constants immediately while evaluating a certain integral, rather we will be doing it at the end by plugging a single constant. So, we will take another example for you. Say we are to evaluate integral of square root of x minus 1 by square root of x whole square dx. So, many times we may not have the application of integrals which we have learned directly. We may have to do some simplification. For example, here if you see, if we expand the square, what we will get is that square root square means x plus 1 by square root x square means 1 by x minus 2 times the product, that is 2. Apply the linearity property here. So, what we will get is that integral of x dx plus integral 1 by x dx minus 2 times integral 1 dx, which you can evaluate as here using the formula x square by 2 plus 1 by x, this is log of mod x, minus 2 x plus a constant of integration. Therefore, this is the integral for this case. So, a problem which may look initially a little bit complicated, but if we use certain relationships which we already know, this can be simplified and further we can figure out that the integral will become very easy. Similar example, another one which I will take for you is, let us take x cube minus x square plus x minus 1 divided by x minus 1 dx. So, it looks a little complicated at the beginning, but if you look carefully you can figure out that in first two terms you can take x square as common. So, that will become x minus 1 plus the second term as x minus 1 whole divided by x minus 1. Now, you see by dividing by x minus 1 we will get x square plus 1. So, the complicated looking term here is nothing but x square plus 1, for which now we can immediately figure out the integral x square, and therefore, it will be x cube by 3 1, and therefore, it is x and constant. So, notice that we have not distributed now this integral over summation, we have directly written it. So, in due course of time with practice you can directly write the integrals, and we will omit all these integral details when we are evaluating the integral. We will put another example for you using some trigonometric relationship. Example 4, say we have to evaluate sec square x divided by cosec square x dx. So, we directly we do not have a formula here, but if we look at this carefully and apply the trigonometrical relationship, that sec square x is nothing but 1 by cos square x, and cosec square x is nothing but 1 by sin square x. So, we can write it as sin square x over cos square x, which is nothing but tan square x dx. Now, again we do not know the integral for tan square x, but we know a relationship of tan square x with sec square x, and we know the integral of sec square x. So, we have to think that what we know and how we can convert the problem into formula or a problem which we already know. So, we know that the formula one plus tan square x equals to sec square x, and therefore, using this formula here we can put it as sec square x minus 1 dx, which will give you. So, integral of sec square x is tan x minus integral of 1 is x plus constant of integral. So, this little bit complicated looking formula, after doing certain calculation, we reached to a relationship which we knew, and we used that relationship and we ultimately found the integral. We will put a comparison of differentiation and integration One is that both of them are operators which operate on functions. Differential is also an operator and integral is also an operator. Operators take functions as input. What I mean to say is that, for example, d by dx of f x. So, it is operated on the function f x, then only it gives you f prime x, and similarly here integral of f x dx, it is operated on the function f x to give you a function f x. So, they are operator. Both of them satisfy linearity property. Integral also satisfy linearity property. This we have seen. Differentiation, if we take of a function, it is unique. So, derivative of a function is unique. Integral, we have seen, if we take the integral of a function, it is f x plus c. So, it is not unique in the sense of the way we define uniqueness, but we call it as most of the time unique up to a constant, which means that if we ignore the constant, then those integrals are unique. You can define the derivative of a function at a point, which means that it represents the direction of tangent at the point, but no such meaning can be assigned in case of integral. That means that integral at a point has no meaning, while differential at a point has a meaning of the direction of the tangent. We also have seen the geometrical interpretation for the integral, for the family of curves, for the case of integral, and similar geometrical interpretation for dy by dx is also understood. We have seen for the case of derivative that it is a limiting process, and same you will learn about integral as well, is that it is limiting process. Finally, as I have already mentioned for one property, is that integrals are considered as inverse operator of differentials, but as I mentioned that they are not essentially exactly the inverse operators because of the presence of the constant. Next, we are going to learn how to evaluate integrals. So, there is no specific method which will be applied to each and every function, and depending on a function or a particular problem, we have to apply different methods. So, we will go through them one by one. The first method which I am going to discuss for you today is method by substitution. As you can see from the name substitution, so what we do in this method is that in order to evaluate the integral f x dx, we notice that the independent variable here is x. We change this variable, independent variable x, to another independent variable t by mean of some relationship. So, for example, assume that x is some function of t which has certain properties, at least differentiability, so that we can differentiate it. Then this will give us dx by dt is equals to g prime t, and therefore, in terms of differentials we can write it as dx is equals to g prime t dt. So, the original integral, if I name it as I, it turns out to be integral of f replacing x by gt dx by g prime t dt. So, the formula for integral f x dx, if I make the change of independent variable from x to t, it converts into another formula of integral of f of gt g prime t dt. So, I will rewrite here integral of f x dx can be written as integral of f of gt g prime t dt. Now, we have already mentioned that these variables of integrals x and t, they are dummy, and therefore, sometime it may also happen that instead of choosing x as gt, we may choose t as gx. That means that t as a function of x. So, some certain function of x we can choose as t, and then we can proceed with that substitution. That will be clear in due course of time. I will take very simple example. So, let us take the example here that we are to find out the integral of 2x over 1 plus x square dx. So, we cannot immediately get this integral by the elementary formulas which we already know, but if you notice that the denominator term here, if you differentiate it, what you will get is 2x, which is same as the numerator term here, and therefore, if you look here carefully, the derivative multiplied by differential can be written as differential in another variable. So, if I think this function as gx, then this is nothing but g prime x dx, and therefore, I can convert it into a new variable t. Let us see how we can do it. So, define t equals to 1 plus x square, or sometime we also say that substitute 1 plus x square equals to t. So, that dt, the differential, we always write it in this fashion, dt is equals to derivative, that is 2x times differential in x dx. So, dt equals to 2x dx. Making this substitution in the given integral, call this integral as I, we shall get I as dt over t, and now this form is converted into the form which we already know, and this will give us log of mod t plus constant. But our problem was in x, so we have to go back to x, and therefore, substitute for t, make it as log of t equals to 1 plus x squared plus c. So, this becomes our final integral for this case. Another simple example, integration of sine of a x plus b dx. So, you can easily see if I take a x plus b as some new variable t, we know the integral of sine t. So, to evaluate this integral, we substitute a x plus b equals to t, so that a dx is equals to dt, and the integral becomes I equals to sine t dt by a, which we will put here 1 by a sine t dt. So, 1 by a integral of sine t is nothing but minus of cosine t, and finally, we will add a constant c, which will give you minus of cos t is already known to us is as a x plus b divided by a plus c. In fact, this relationship can be generalized, which we will see in our next class, that if we are given a function which is having linear term as a x plus b, then it is always the integral of that function divided by the constant. So, we shall summarize whatever we have learned today. So, we learned the properties of indefinite integrals. We also learned some elementary formula. We learned how to evaluate simple integral. We also learnt the comparison of differentiation and integration, and finally, we learnt the very important method of substitution. Thank you.